learned a lot about. So yesterday we learned a lot about Cytoscape, the disease map projects and WikiPathways, and today we're going to actually use the skills that we learned and the resources that we have and dive into some of the automated workflows. So very quickly, we will have 3 examples of automated analysis workflows. They're implemented in R, but it can also be implemented in Python or other languages if that's what you prefer. We will use pathway information from the COVID-19 disease map and WikiPathways. And we could extend that or apply that to different sets of pathways as well. So if you would have a collection linked to a certain type of cancer or to immune pathways only, then you can do the same approach and only focus on that subset of pathways, for example. How will this work? So each workflow comes with an RMD, so a R markdown file, which means that the R file has textual descriptions as much as code samples. That means it really guides you through the workshop and tells you what you should do in each step. There is one data zip file that you download with the first workflow, and that contains all the required files for all 3 workflows. So if you put all the RMD files in the same folder as this data folder, then the folders will have access to that data folder. And what you then will do is you open this RMD file in RStudio, and for each section you have a description of what the section is about. Then some code blocks will need to have need you to change or write some code. You can check that, and some you might just need to run. And then there are questions below the code block. Those might be technical or biological. And you can answer them. Some of them you might need to write some code yourself or look at some of the data files that data objects that you created in that section. And some are really more looking at a figure and interpreting what's happening. And once you're done, then you move to the next section. I will open one example so you can have a look at how this looks like as well. What we're going to do today as well is we're going to do this in breakout rooms. So I think a little bit of interactions for these questions specifically. We're going to work in breakout rooms with 2 to 3 people each. Please, in the breakout rooms, turn on your videos, share the screen, discuss what you're doing. You will get more out of it, and the other people will get more out of it as well. In the breakout rooms, there's a button in Zoom at the bottom then, only once you're in the breakout room, that's called Ask for Help. So if you're in a breakout room and you're like, okay, we're stuck, we don't know how to continue, you can simply click the Ask for Help button, and then one of the instructors will come by. In case we're all busy, it might not be immediately, but we know that you called us and we'll come as soon as we have time. This will hopefully encourage some discussion on the question specifically. So what are the workflows we're looking at? So the first workflow is the typical enrichment analysis part, but it also shows you how you can visualize the pathways with the Cytoscape automation feature and extend pathways with drug target information. So as an example, these are the steps. So we will use the data set that Lauren described so nicely yesterday of the bronchial cells, the NHBE cells. One group is infected with SARS-CoV-2, the other one is infected with a mock infection. And so we will use that data set to first do a differential gene expression analysis. So we will compare COVID-19 versus non-COVID-19 using certain R packages. Then we will integrate the pathway content from the disease map and WikiPathways. And then we do overrepresentation analysis. So the typical enrichment analysis. In theory, you can also replace this with other enrichment methods that's also described in the text in the script. We will then visualize this enrichment result to see, okay, which pathways of the COVID-19 map are actually enriched in our data set. And we will open pathways in Cytoscape. So make sure that you have Cytoscape open again, like yesterday when you did the automation with Scooter. For all the workflows, you will have RStudio and Cytoscape open. And we will visualize the pathways in Cytoscape. Sometimes there's a question, create your own visualization or try to write some code to automate that visualization to see how you would visualize that data. And then the last step in that workflow is that we will first we visualize the pathway as a pathway diagram. And in the last step, we will visualize the pathway as a network. So in a network view, and we will extend it with drug target information. The second workflow is a PPI focused workflow. So we will also use string like you did yesterday as well. We will use the up and down regulated genes from the same data set as before. We will create a protein-protein interaction network using R-Size3, so all automated in R, using the string app. We will then also think about how can we visualize this the best way? Can we maybe use a gradient to visualize the up and down regulation and so on? And we will extend this protein-protein interaction network with information from the COVID-19 pathway collection. So we will then know which proteins that are up and down regulated are in pathways and which ones are not. And maybe there's a pathway missing in our pathway disease map. And that analysis, for example, helped us to prioritize curation efforts. So we're doing this with a lot of different COVID-19 data sets. And then if genes show up very often as deregulated, but they're not in our pathways yet, then we're missing a process that is definitely affected. And then the last workflow is a pathway crosstalk analysis. And I adapted this one a little bit. I gave it my best shot, so I hope it works. We're looking at a crosstalk between pathways. So there's a lot of overlap between the pathways. So we're going to do a topological analysis. So we will create this COVID-19 pathway crosstalk network and do some topological analysis. So we can look at the degree and the petriness, these measures that also Scooter explained yesterday. So we will look at, okay, which genes are in a lot of these pathways and which pathways have a lot of genes and interactions like that. Then we will visualize a multi-organ proteomic data set. So in this case, there is a paper where they did proteomics data analysis of COVID-19 patients, and they measured the expression in different tissues for COVID and non-COVID patients. And we're basically gonna visualize that data. I picked 3 examples, lung, liver, kidney, and I didn't pay a lot of time on making that data really nice. I'm basically just using one patient for each organ, so that can be improved, obviously. But we're going to try to make an animation out of this. So we're going to have lung, COVID versus COVID and non-COVID. So it's not a versus, so it's not a differential analysis, but it's baseline expression. We're going to have liver, COVID and non-COVID, and we're going to have kidney for COVID and non-COVID. And then we're going to visualize them and see how the network changes over time. And I also thought that this is a nice opportunity to show you a little bit about enhanced graphics. So we can actually visualize a heat map on the nodes where we can then see the expression values next to each other in one visualization. So for a publication, obviously a video would be nice for a website, but not so useful for a publication. For a publication, if we want to compare different organs, then maybe an enhanced visualization in Cytoscape like a heat map is one way to do this. This is the introduction that I give you now, but after we actually go through the workflows in the wrap up, I will walk you through the workflows as well. So you will see how in case you didn't manage to go through all of the steps, I can then also explain some things when we go through the workflows together. Now, very quickly, I'm gonna share my screen of the website itself. And I'll show you how this looks like and how to get started. So if you go, Lauren, if you could post the link again in the chat, that would be great. If you go to this original page that we have, we're now in the second day, already uploaded the slides, and we'll start with workflow 1. So we can simply click on practical here, and we see what we're going to do. So we have the differential gene expression analysis, pathway enrichment, and pathway visualization. Lauren will create the breakout rooms, and we will randomly distribute people in these breakout rooms. I think 2 to 3 people is enough. And this is the workflow that we will start with. So you can keep this open. This is kind of the nicely formatted information. But here in the top right, you can click on download RMD file. And that's the file that you can then open in RStudio. Additionally, here you have the data zip file. So if you download that zip file and extract it in the same folder as the RMD file, then your RMD file knows where it can get the data from. The workflow itself, some things you will just run. So if you open this in RStudio, you will just have a run button. So let me show how this then looks in RStudio if you open it. Let's see if I can make this a little bit bigger. I don't know if you can read this, but so if you have workflow 1 open, then you will see that certain sections you can run. So there's this green little play button, and so you can run the current chunk of code. And then you can run the next chunk of code. Again, make sure that you have all the libraries installed beforehand. Just as a reminder, all the packages that you need and how to install them is here in the instructions, preparation instructions. So you run each section after the other, read the instructions again, and then sometimes there's a question. So here, how many samples are in the data set? And then you will need to explore the data. So you can have a look at the data and see how the data looks like and discuss with the people in your breakout room how this is actually going. This is basically how to get set up. We're now going to create the breakout rooms. Maybe we make 3 breakout rooms. Yeah. And then if you need help, you simply ask the help button, push the ask for help button, and we will come by and answer any questions. Are there any questions at this point that you want to ask right now?
Do you have Jupyter Notebook instead of RMD file?
A what? Sorry.
Do you have Jupyter Notebook instead of RMD file?
Not of these files now. But you could copy them over, I guess. If you have Jupyter Notebook installed, you just need to copy the chunks over, I guess.
Got you. Thank you.
Yeah. So yeah, this time I just, because installing Jupyter Notebook locally is not everyone has that set up. So in this case, I did the RMD files. It's a nice idea to add actually the Jupyter Notebooks as well. But for now, it's the RMD files. So not sure how easy it is to quickly convert it into a Jupyter Notebook.
Thank you.
But you could copy it over. Any other questions at this point? Then we're going to put you into breakout rooms. Please, when you're in the breakout rooms, really try to turn on your camera, try to interact and discuss what you're doing, and walk through the workflow 1. We will get back together. Let me quickly check.
What is the time frame like for each?
Yeah.
Work,
so we have
like
about 45 minutes per workflow, approximately. So if we try to get back here at, UTC time 4 o'clock, I don't know what time it is everywhere. So in about 40 minutes or maybe 5 past, then we can continue with workflow 2. And as mentioned at the end of the wrap up, I will walk you through all of the workflows so we can see how it went and how it but this is kind of a time for you to play around with the workflows now. If you have questions, don't hesitate to ask us. So just put the ask for help button. And we will let you know, usually it's about a minute until we close the breakout rooms. And that will be about 40 to 45 minutes from now. Then Lauren, please, if you can open the breakout rooms. Then everyone should have an invitation to go to one of the breakout rooms. And I hope that it's not too small, but I want to show it in parallel. So you'll see Cytoscape on the left side and RStudio on the right side. I'm just going to start from the start. So I just load all the libraries and set the working directory. And so then I load the data set. This is just loading the data frame and then doing some pre-processing, so some formatting of the table. So if we now look at the table, if I run this code here as an example, the dimensions are 21,000 genes, something like that. This is how the data frame itself looks like. So we have the genes and in the columns, and then we have the different data points. And this data.call object actually tells us what kind of conditions we have and how many samples we have. So we have two conditions, NHPE mock and NHPE SARS-CoV-2, and we have 3 samples each. So it's a quite small data set. Then we do the differential expression analysis. So with T8-II, but you could also use Azure or other, if you have not RNA-seq, but microarray data, for example, you would use Limma. Just running through that. And also adding some other identifiers. So here we have identifier mapping. So we're going to also add oncogene identifier and ensemble identifiers to make sure that we can do that mapping. And do some renaming of columns and write it out, because we might need it in workflow 2 and 3. Then we could check how many genes are up and down regulated. So if we look at this data set now, we see here the gene ID, the gene name, and then the log fold change, p-value, p-adjusted value, statistics, and the ensemble value. And maybe for now I'll still make it big, so maybe that's easier to read, but I'm not sure. And what we'll see is that some have NA values. Those are usually genes that are filtered out because they're too lowly expressed, or that there were really strange outliers that they just don't trust that p-value, that enrichment analysis, basically. But for a lot of the values, we have a good differential expression. We can sort this also here. So we see some genes with a very strong down regulation or a very strong up regulation in SARS-CoV-2 exposed cells. Just to show that we could also visualize this, we can make, for example, a volcano plot out of this that might look like this. What we do see is that there's a lot more up regulation than down regulation. And maybe if I zoom in, we see here SAA2 and CCL20. Those are really significantly upregulated genes. If you, for example, go to PubMed and just search for SAA2 and COVID-19, you will find immediately a paper that says that this gene is a biomarker of severe coronavirus disease and poor prognosis. So you can then really see, okay, what genes are changed? What are they doing? Do they already have a link to this disease? Yes or no? Then, yeah, and so you can explore this a little bit more and see what kind of cutoffs you might want to use. So in this case, I used a cutoff of 1 point as an increase of a fold change of 1.5, so a log fold change of 0.585. So it needs to be at least half as, like 1.5 times as expressed, or half as expressed than the non-COVID data.
So it is like absolute value.
Absolute value of 0.585. Yes. So this is basically this line that we see here for the log2 fold change. Indeed. And for RNA-seq data, you might actually go lower. So you might just go for significance as a cutoff, or you do that cutoff. It really depends on the data that you have. For microarrays, you usually have some fold change cutoff to make sure you don't have too much noise included. Yeah.
The color. Sorry, the color here, the red and the green and the blue. So it just confused me. Like so we have different color for the fold change and different color for the p-value.
So what this means is, so I have a cutoff on the fold change cutoff. So these are these vertical lines, and I have a cutoff on the horizontal line, right? So significance of 0.05 of a p-value. So the red ones fulfill both these criteria. So they are significantly changed and they have a fold change above the value that I defined. The blue ones are significant, but they have a lower log fold change. And the green ones are not significant, but have a higher log fold change. And the gray ones don't fulfill either. So you have different possibilities, let's say like this. So there's also quite some genes that are strongly changed, but not significant. And that's because we only have 3 samples, right? So there's a significance issue as well. Then we move to the pathways, right? So we want to include pathway information. And we're going to integrate the WikiPathways collection of July this year and the disease map, COVID-19 disease map of June, the June release. And what I do is I read the gene sets in and I kind of merge them into one. So if I look at this data frame, I have a pathway and a gene. So I now know in which pathway which genes are present. If I want to know which pathways are present, then I would need to do something like a unique WPID name and WPID. And then I would see, okay, these are all the unique pathways. And then if I would do a length, instead of just printing it, then I would know how many pathways are now in this list. And that 706 pathways are now included.
Excuse me, can you tell me like what the GTF, this is the first time I saw this file extension. So the first one include the pathway from WikiPathways.
So these are typical GMT files. Yeah, so GMT files are gene set matrix transposed. So it says pathway and then all the genes in separate tabs. So it's gene sets. And we just convert that into a table. Okay,
so the first one is pathways.
Both of them are pathways. And the first one is from WikiPathways, and the second one is from the disease map. So it's 2 different resources that we want to combine in the analysis.
Got you. Got you.
Yeah. Felice, there was a question about the log, about the fold change cutoff. So a log 2 fold change of 0.585 is a 1.5 fold change. So this is with fold change cutoffs, you either go for 1.2, 1.5, 2 fold change, and so on. And the log 2 of that is 0.585. So it's always in log 2, even though here it says fold change cutoff, it actually means log 2 fold change cutoff. I hope that explains it. So it would be a fold change of 1.5. Okay, great. Now we have our pathways and we have our data. So now I just chose to use the same cutoff as we had before. So I do a log 2 fold change cutoff absolute of 0.58 and a significant p-value and run the enrichment analysis. So this is a typical over-representation analysis. I want to know, are there pathways where there are more of these changed genes present than I would expect? And then you get a table. So I can just say EZP res. And then I see, okay, okay, maybe if I make it bigger, I can see it or not. Yeah. This pathway is significantly enriched with this p-value, and it has 13 of the 223 genes that are significantly changed in the background. 34 were measured. This table is nice, and it's actually very often included in papers that you see this as a table. You could also look at this from a visual perspective, and this would be the table view of this. So it's the same list of pathways as we had above, photodynamic therapy induced, so IL-18, vitamin B, the infrared lambda pathway, and so on. But now we see the list basically visualized with a box plot, bar plot.
I have a question. If you go up to the function enrich, what is your onBot list and what is your background?
Yeah, so the differentially expressed genes I just defined as the same criteria as we have for the volcano plot, the absolute log fold change of log 2 fold change of 0.58 and the significant p-value. But you could also do other cutoffs here. And the background list is all the measured genes. So all the genes for which I had data.
The 27,000.
7,000 that were in a pathway. Yes.
And what about this term to gene and term to name? What is this? The two.
So the gene ratio means 223 of the 7,411 genes measured that were also in a pathway were differentially expressed. So they were in my input list.
No, I mean these two parameters.
Up here. That's the definition of the gene sets. So you tell the program what pathway gene association you have. So which gene belongs to which gene set. That's the format. That's why we formatted our data to this. If you look at the data frames, it will be very logical. It's just a formatting that you need to do here.
Mm-hmm.
And then we see a lot of immune-related and COVID-related pathways popping up. We have here a type 1 interferon pathway. We have the Minerva pathway from the disease map from interferon lumbar pathway. We also see NF-kappa beta pathways, a lot of immune response, and so on. Coagulation, complement activation, some metabolic pathways, and so on. So this is pathways we would expect to see changed.
Do we need to include the p-value here or no?
You can visualize also the p-value. In this case, the p-value is significant. So these are only the significant pathways. But you could also visualize that as a gradient, for example. Yes, indeed. And then how can we visualize this? So now I'm going to try to do this in parallel. I'm going to open one of these pathways in Cytoscape. Yeah, that's one of the pathways. I load the data table, and then I asked you to maybe come up with your own node color mapping of how you want to maybe visualize this. In this case, I added an example. So what I would usually do, as Scooter said, to write this one, I go to Style, and I make the fill color how I want it to look like, and then I copy it over into my command. So I know what I want. So what colors do I want? What values do I want? And so on. I test this here. How does this look like? And then I automate it here. So it's the column log 2-fold change. I want it from -1 to 0 to 1. I want it from blue to white to red. It's a continuous mapping, so it's a gradient. I want a default color of gray, so I know immediately this has not been measured. And to which style do I want to apply this? And what we now see in this pathway is there's a lot of red in this interferon pathway, so a lot of upregulation. So if we look in the style again, positive log 2-fold change means upregulation. Some genes are downregulated, like TLR3, I think, and so on. But since it's immune pathway and it talks about innate immunity starting up and so on, the upregulation makes sense in a COVID-19 setting. So the virus triggers the immune response in these cells. What we can also do is look at this pathway from a network perspective. Scooter mentioned that last time already. Not ideal for topological analysis, but what we can do that is indeed quite interesting is extend the pathway with additional information. So now I'm running, oh, I should have uncommented this because the apps are already installed, but the apps get installed again. I hope. Let's see. Yeah. Now I'm importing the same pathway as a network. This is how it looks like. And now I'm running here in line 269, the command to extend the network with drug target interactions. So in this case, we use drug target interactions from drug bank. And I also added some nice bypass rules for the drugs. So I wanted to show that you can use bypass. You could also make mappings for this, but you can bypass. So I selected all nodes that were drugs and then use the bypass column. So the bypass column is also seen here. It's overriding the mappings. So now if I select one of these drugs, I will see that I have overwritten these settings by running this a couple of lines here. And I now see the pathway and I see that certain genes, like here in the top, INFAR1 and INFAR2. They're targeted by a lot of different drugs. They're in this case all interferon alpha and so on drugs, but also down here we see some chloroquine was discussed a lot in the news, so we know a lot about that, hydroxychloroquine and so on. So there are some drugs showing up with their targets in the pathway that we're looking at now, and we can do this for every pathway. I can also then load the data, and I'm a little bit, let's see, WikiPathways as network. Here I need to adapt this as network to also visualize the gene expression on the network, which now shows up. So now I have the drugs and I see what's also happening with the target. So for example, for these drugs, the genes are only, or the gene expression is only slightly elevated, but maybe for this one, it's strongly elevated. And so maybe some of these drugs that target some of these genes, for example, this one down here, might be interesting to look at in case they're inhibitors, something like that. So you get a feeling of what's happening. And you can do this for every pathway separately. You can even merge pathways and do the extension. You can do this extension with protein-protein interactions and so on. So this is one way to analyze this. In the end, in the script, I always have a way to save the session, save the visualizations, just as an example. As Kuda mentioned yesterday as well, always make sure you zoom in enough when you create PNG files so they have high enough quality. Save the session and then close the session before, so you restart fresh in your next workflow. That was a quick walkthrough, not as quick as I hoped, but it's time to move on with workflow 2. In case you have questions, maybe we'll keep them for the end. Okay, so now we're talking about workflow 2. So we are talking about the protein-protein interaction network. So I opened the workflow solution again, the workflow RMD file and the Cytoscape again. I'm going to run through the setup just so all the libraries are loaded as we need them. And then we're going to load the data. So in workflow 1, we wrote out this file, differentially expressed genes /data, and we can read it in. And then I also select my differentially expressed genes again with the same cutoffs as before. So a log fold change cutoff and a p-value cutoff. Then I'm going to create a protein-protein interaction network, like Scooter also showed you yesterday, but now with the COVID relevant genes. Interesting. I'm going to, sometimes Cytoscape needs a restart for some reason. I'm quickly gonna close this one. I'm gonna start it again. What we're gonna do is we're gonna write a string protein query. So we look for proteins with a cutoff of 0.9. That's a very strict, high confidence cutoff. And I give it a new network name, which is just protein-protein network. And my query is the list of all the differentially expressed genes, and I use the gene identifier. So the onto-gene identifier. So let's see if this command now runs.
Which function you are using for this query?
Which function? So I use the string app. So I use a commands option for R-Sci3, and I say string protein query. So it's like the same as if I would put it in here.
Oh.
String protein query. I put my gene list in here, and I select. It's now still loading, so that's why it's And I select here a confidence cutoff of 0.9. That would be the equivalent of what I write here. I could also do a disease query or a PubMed query or a compound query, but we now selected string protein query. Then we define the cutoff. we give it a name, and then we paste in here basically ABC, the genes, in this case with the gene identifier.
Good.
And then we get this string network out. In this case, it's 0.9, so it's a very high confidence cutoff. We see some nice clusters here, so we could do some clustering if we wanted to. We see a lot of unconnected nodes as well, so that means these nodes have no direct functional relationship with the high confidence. So one of the questions here below is what would happen if I would do a 0.4, let's say a medium-sized cutoff. If I run this query, for some reason it's making troubles now. I think string, I might have asked too many times something to string, so it doesn't let me query it anymore. Okay, so what would happen if I would do it with 0.4 is that I will have a lot more connections, because then I'm not as strict with the cutoff. So I have more edges in my network, the same amount of nodes, so 424 nodes, but a lot more edges. I can test it later on and try it again. What we can then do is load our data again, right? So we have now proteins instead of pathways, and we can simply load the table again, our gene expression data, put it on the network. What actually happens is that here in the node table, let's see if I can make this bigger again. I see here the columns that are in my data file. So if I go to the data file here, let's see, should be this one, I guess. No. Yeah. These columns are now added here in the node table as well. Whenever there's a match between my gene in the network and my gene in the table. And then it just adds that line into the node table of the network. Some have no values, I assume, if I scroll down, or in this case, all of them have a value because I put the list in of all the differentially expressed genes, so that makes sense. We do see that there is up and down regulated genes in here. What we see nicely is that some of the upregulated genes cluster very nicely together. The downregulated gene seems to be more connector nodes here and there. So we could now do an enrichment analysis or something like this to see what processes are affected. Or we could look, for example, in this situation, okay, what is this cluster? What genes are in there? And we see again a lot of immune-related genes, IFI44, IFI27. So this is this typical immune genes that pop up. So this is one way to visualize it on the protein-protein interaction network. By the way, in string, you can also remove these kind of glass ball effects that they have. So now this is gone. It depends on what you want to do. Now, by default, it shows the protein structure. Now it doesn't show the protein structure. So it depends on what you want to highlight. Then let's see. What is the next step? Yes, so these are the protein-protein interactions. And something that might be interesting when we want to figure out what are the things that are changing, which we don't know anything about yet, is can we extend this this network with pathway information? So if I now run this, I'm going to use a target linker to extend the network with pathway information from the COVID pathways. So the COVID pathways link set contains gene pathway associations from WikiPathways COVID portal and the disease map, the COVID-19 disease map. So it's only COVID pathways. And I extend the protein-protein interaction network with that information. So then I will know which clusters are already in pathways, which protein interactions are well represented, and which information is not yet at all in any of the pathways that we have in our COVID collection. That really helped us. So we ran this analysis also for purposes of curation efforts, right? So what are the things we want to curate? What we see is that there's quite some immune-related pathways in the center here. So as you see here, this is a specific RAS and bradykinin pathway. Here we have some innate immune response and so on. Some have more genes, some have less genes. but there's still a lot of genes that are not present in any pathway. For example, this whole cluster here is very strongly upregulated, but not present in any COVID pathway at the moment. So from a curation point of view, that becomes very interesting because there's some molecular process that is affected, but that we don't have mentioned yet in our map. So this is one way to identify things like this for curation focuses, but also to see how much overlap there is between the differentially expressed genes and the pathway information. And then in the end, I can again save the images and the session and close the session to see, to start fresh with the new one. Are there any questions about this workflow? So this workflow will, first of all, give you a little bit of context within your disease map, similar to the functional enrichment, but then really adding it visually as well. We could do a degree analysis to see, okay, which pathways have most of the differentially expressed genes and things like this. Something that I did want to show is something that we mentioned yesterday, right? So this visualization, one of you asked, how can I get rid of the overlap? In this layout, which is the force-directed layout, there's a lot of overlap. And I mentioned this Y files, if you have the Y files layout app installed options, and there is one for remove overlaps. And if I select that one, and I now zoom in again, it actually gets rid of this overlap quite nicely without losing the structure too much. So now it's a lot better aligned. So this is actually quite useful tool if you have this overlay in your network a lot. Just as an example, the Wi-Fi's layout cannot be automated, as far as I know. That's a licensing issue. So that means that you can only do it manually.
So now from this network, the color represent the logfold change and the
yeah. In this case, I used the same setting as before. You can obviously make this a lot bigger, right? So let me give an example. I could now say, okay, I want to change the style of the shape because I want to make the, we have a type here somewhere, I think. No. Let's see. CTL type. For example, we want to make the pathways as an octagon. So then all the pathways would be octagons. We might want to change the color of the pathways or the size. Maybe we want to make the gene smaller than the pathways, you know, things like this. So I could make a mapping here for the type to increase the pathway nodes and make the gene nodes smaller. So I make the gene nodes smaller and I make the pathway nodes bigger, something like this, right? So you could play around with these kind of settings depending on what you want to highlight. And as Scooter mentions, I usually do this first by exploring this once manually, and then put it into the code to reproduce it later on. But some visualization tweaking will always happen in the end. So it's rarely that my publication figure is fully automated. It's mainly automated, but especially layout and stuff, you still need to tweak once in a while for the publication figure itself, let's say. But there's a lot of options that you could do. We could also show the border paint. For example, we could show the p-value for the border paint or anything like this.
Okay, so how can I, from here, how can I say what is the common pathway for most of the differentiated genes? Like, can I say some hub?
So what we could do, yes, what we could do, I just need to move this the Zoom thing a little bit. What we could do here, let me check the correct one. Yes, I could type. I could call the function analyze network, right? And I could do that as an undirected because it's a PBI. But what happens then is that it adds all these degrees and stuff like this. So betweenness and degree and so on here. So I could filter for the CTL type pathway. So I only want to know about the pathways, right? So I filter the pathways and then I sort by degree. Right, so I see that, for example, the SARS-CoV innate immunity evasion and cell-specific immune response pathway has 12 differentially expressed genes. So I could select that pathway and then could select, and I can automate all of this, but I didn't plan this now. So, and select the first neighbors with the genes and then create a new network from these, from this subnetwork. And then I could, for example, see how the genes in the, need to remove this window again. How this pathway has the differentially expressed genes and how they're connected based on the PPI. Does that answer the question?
Yeah, if I go to the previous network, can I see like a hub pathway, which is like most of the genes they involve in that pathway?
Yeah, so what I could do is use that degree as a size, for example. So instead of doing this, I could now use the degree, but it will also make the genes big, so it's a little bit tricky. Let's see, where do I have the degree? Current table, in which network am I? Oh, here I am. That's what I need to do. Degree, and then I could do a continuous mapping, and it would become bigger and bigger and bigger. But then that's only for the genes also involved. So we have a maximum of 12. So I would need to set min and max from 0 to 12. And then also make this a lot bigger. So from 40 to maybe 80 or something, I don't know. And then we will see some bigger pathways show up. Some are smaller, some are bigger. Does now actually work? No, now it reverted back to what it was there before. Okay, let's try this again, 0 to 12. And then here, maybe 20, and here, 50, and okay. And now we see the big pathways here. Those are the ones that have a lot of genes. And we also see the genes that have a lot of connections to other protein and pathways.
Got it.
So that would be one way to visualize this. But the easiest would probably be with checking the degree of the pathways and then highlight them specifically.
Can we do like what Scott showed us yesterday, the donut things, which is like yesterday he showed us like how to put the Go terms like circle.
This could be done with the string app. I just need to check. I'm not sure if this is now still considered a string network, so I would need to check. Okay. I'm not sure if it's running now or not. But yes, the answer is yes. You could also do that now. You can do the same things as before. But somehow it doesn't run now. The visualization of this, of the processes I would do on this one though, right? So if you would do it on here, let's see if it now works. Somehow I don't see it showing up, but let's try to select them.
I think you've got something strange going on with your string app.
Yeah, I don't know.
Yeah.
So yes, usually you could do this and then you would see the result and could make the thing. I needed to restart it now twice because it couldn't make the query. So I don't know what is going on. Maybe I made too many requests now.
You can take that. You can look at the errors. See the little error dialog.
I will check that later on. Yeah. But in theory, it's also just a visualization style, right? So you could also add it there if you want to. But this is workflow 2, more or less. There's a lot more that you can do, right? From clustering to more advanced visualizations and so on. but it gives you a starting point. And this is one way to check what do we already know in mechanisms from the disease map project and what is changing where we don't know the details yet. So giving you a little bit an idea of where more research is needed in the situation of COVID. And that's workflow 2. And now I would propose to maybe keep the break to a 10-minute break for a quick coffee refill and bathroom break maybe. So we can continue with workflow 3, which will be about pathway crosstalk and visualizing proteomics data from different tissues. And so we'll see you at 7, or yeah, I don't know what time it is at whatever hour it is at your place, 25. So in about 10 minutes.
So we need on.
Everyone back already? I think so now. Okay, so we have the third workflow where we look at overlap between pathways and a little bit more advanced visualization, let's say like this. So I'm going to again start the setup just so I know everything is set up properly. And we'll start by creating a pathway gene network. So I selected all the COVID-19 related pathways that were created within the disease map project, and I create one large network. If a gene is present in 2 pathways, it will have edges to 2 pathway nodes. So let's just load that network. I first create the edges, the edge list, then I create the node list, and then I create the network from the data frames here very nicely. I also show you how you can add the gene names, for example. There's a lot of different identifier mapping tools available. Cytoscape also has one integrated, so you can also use the map table column to map from ontogene to HTNC, for example. And this would be a way to how to merge 2 columns. So if you have the name for one element and HTNC column for the other, you can merge them together in a label column. So now I have this new label column, which has pathway names or gene names or gene identifiers if there's no pathway name. And I also, in line 80, analyze the network. So the network analyzer calculates all these network properties like degree, betweenness, and so on. Since I have pathways and I have genes, I actually did a directed network analysis. So I split up between in degree and out degree. If the in degree is present, then it means that a pathway is connected to a gene. So this gene is present in one pathway. The out degree means how many genes are in a pathway. So for example, in this Minerva pathway for electron transport chain, let me go back for the out degree. There's 210 genes present in that pathway. So it connects to 210 nodes. Then in the next session, I actually asked you to come up with your own visualization. Can you come up with a nice visualization? So I did some initial checks on what I could do. Let's see if this runs fine still. I created a new style. I did some nose size mapping. I did some nose shape mapping. I did some node label mapping and some color. Let's see if that all loads. And then line 105 to 108 here, I used to highlight, for example, what was asked before, something like hub genes. Can we somehow highlight genes that are in a lot of pathways? And I did this with the border width. So I selected nodes with a high degree, high in degree. So these would be these, maybe I should make a bigger node width. So it's a little bit more visual. Yeah, these nodes with the green border color here. Those are the genes that are present in a lot of different pathways. The blue ones are the pathways, the red ones are the genes, the bigger the genes, in more pathways these genes are present in. This would be a typical network where I would again run this remove overlap algorithm to kind of make some space and see that now there's a couple of pathways that really share a lot of these genes here in the center. And as we would expect for an infectious disease, a lot of this has to do with immunity or immune response. So here we have SARS coronavirus innate immunity. This one is the type 1 interferon induction that we looked at before. Here we have the interferon 1 pathway from Minerva. Here we have the interferon Lambda pathway. So there's a lot of crosstalk and overlap between these processes. Now we have a data set that contains proteomics data. So I'm going to run quickly this, and I quickly wanted to show what this data looks like. So just going to go to data. Oh, there's still something running. Let's see. Okay, I'm just going to restart the session. Let's see if that works. Sorry about that. Yes, so here we are. No, this is still the gene expression data. Yes. So now I'm gonna try this again. I'm gonna load the data for the protein expression data. So I just took examples of this large paper, right? So this is not all the data, obviously. This is really just individuals that I picked out. I have examples for lung tissue non-COVID patients. I have examples for lung tissue COVID samples, so COVID patients, and the same for liver and kidney. So these are protein abundances. Some are not detected, others are detected, and I did a log 10, so it's all between 0 and 1 to kind of normalize the visualization. So what we can now do is we can load this data onto the key column and then create a visual style where we actually use the table, the node fill color for the gene expression data. So I'm just going to show you now how this would look like before I make the whole visualization part. I'm going to create a new, this would be the example for the lung COVID data set.
I think you need to restart the Cytoscape because you need to start from again.
I think in theory that should be fine, but let me see if it loaded. It did load the data, so that's not the problem. Somehow it doesn't. Oh, I'm in the other style, obviously. Yeah. So I created a new style called My Style Lung COVID. And what you now see is the style goes from white to purple. I should probably change the default color, but since I changed the size, you don't see the differences so strongly anymore. So I'm going to change the default color here to something less strong. What you see now is the darker the color, the more expression the protein has. And in this situation, we might even want to remove the label or other things to make it really visible. So if we look, for example, would remove the labels, then we could have a better overview of what's actually happening, right? So there's different ways on how we could do this, but this is just to show you a little bit on what we can do. So if I run now this whole script, I basically create a video, as Kuder mentioned as well. So here I define this new style, I apply the style, and then I run the CyAnimator recording part. So here I always capture it with 60 frames per second, or yeah. And so let's see if this works. This will take a while, but it's still kind of cool to see how it works. So first we're gonna load the file. We're gonna create a visualization for that specific tissue. We're going to apply the visual style, and then we're going to capture it, and we're going to say, hey, that's the first screenshot. Then we're going to create the same for the non-COVID. So it will look slightly different. Obviously, now it's going to be blue as the default color again, because that was what my default style was, which is not ideal, but we could change that. We should change that.
So Martina, so what are you trying to see? The difference between the tissue or between COVID and non-COVID?
Yeah, I did hear the example of both. In theory, you could also do first just COVID between the tissues. Now I just wanted to show how you can see the switch between them. So what I would do if I would really create a video is probably I would make one for COVID comparing the tissues, and then having one where you go from COVID to non-COVID, something like this. But I just wanted to see how you can see different visualizations, let's say, attached after each other, and made a video out of it. The choice of the blue default color for my style was not the best, because now you don't see the purple very well. But I changed that now because I wanted to show a couple different options. But we will see it what happens in the animation in a little bit. So now it's writing out images. So if I now go to downloads and let's see, and test, you will now see that it creates these frames, and it needs to create a lot of frames for each part, so it will take a while. And then it's going to make a video that goes from one frame to the other. And you see that in the beginning it's still without the blue, and then because the first one I didn't have with blue, and then the others I had with blue. So the other sessions I had with the blue color. So we'll see how that looks like. But this is one way to visualize it in a video. It would be much cooler if you, for example, could do a filtering if the protein is expressed or not, and then hide the note if it's not expressed, for example. And then you would really see a change in notes appearing and disappearing when you move between the tissue, but I didn't have enough time to implement that properly. But that would be the approach I would take, to hide the ones that are actually not measured in the pathways or not detected. Yeah, so I guess this really will take a while because now it needs to create a lot of frames. But then you get this MP4 video where you can then really go through the video and see how it changes. Is that clear for everyone what has happened? Because I might stop it now because it's going to do this. No.
Please keep it going, because we need to see how it looks like.
Yeah, so basically what will happen is this. It will walk through and move from one to the other and change into the next one, and change into the next one, and so on. So you see changes happening as they go, but then in one video.
Okay, so we are seeing that in this video what is the conclusion statement you need to make from this video? You need to say, okay, look at this protein, how they change.
Exactly. So what
COVID, non-COVID?
Yeah, so what I would do actually is, before I capture this, I would probably, maybe we can try it as well. I would probably select all the nodes that have no expression for long COVID and hide them. So then the network structure will also change, and you see how certain areas become more active in one situation compared to the other. But yeah, I didn't have time to implement this, as mentioned. I only got the idea yesterday that example. It's a good question, Gurpreet, about the videos for publications. There's some journals that start to allow videos and things like this. But the significance of this video is, first of all, you might really see a change that you want to visualize that way, and you want to use that as a kind of snapshot of your analysis and upload it as a video to the publication. Might also be something for just on Twitter to kind of, you know, announce, or on social media. This is the paper and this is a cool visualization thereof. So it depends a little bit on the use case that you have. But I think that if you would actually remove the nodes that are not abundant or not detected in a specific tissue, but they are detected in another, you will really see that switch in network structure. And I think that will make the bigger difference. Now, with all the colors and the size, now it's a little bit difficult to see. So I agree. Now, this specific video might not be the most useful immediately. I'll try to make a nice one and I'll send it and see. Then you can see what I mean with the hiding of the nodes with the script. I will upload that to GitHub as well. Then you can see it. Now I know how it works, but it took me a little while to come to this already. But now we can create these frames, and then we switch from one tissue into the other. And we might see that one pass we only detect 2 genes in the COVID, but 20 genes in a non-COVID. And we suddenly see that there is a real change happening on the network structure.
Often what you'll see in something like this is, if there's an area that's really of interest, what you'll do is zoom into that area and then do the transition through that zoom. So you can say, that way you can see in this pathway, you can see between these 2 tissues. And then if necessary, you can zoom back out and zoom into another area. So all of the kinds of things that you would normally see in an animation, you can do because it tracks the presence and absence of nodes. It'll fade them in and out, and it tracks the zoom level.
So can we use this without RMD file? Can we use it only in Cytoscape?
Absolutely.
This is all the SciAnimator app. I'll show it the moment it's finished. It's that's the disadvantage.
I'm wondering why in my case it doesn't get a lot of time like yours. Oh.
I think in a lot of cases, the first thing is to try this, going through it manually, and then try and script it. I mean, I'm pretty sure that's what Martina did to begin with.
Yes, I did.
So
and
how
the manual approach, it does have a reasonable interface that allows you to give the timing and control the timing and things like that.
Yeah. So maybe initially I wouldn't do the 60 frames or something, but something quick to see if I can see that change, yes or no. But yeah, this takes now a little bit longer than I initially did it with a lot less, so it takes a while to render now, but that's okay. And I'll, once this is done, I'll also show the SciAnimator. It's basically the same thing. You select what you want to see when, you click, okay, capture this one, capture the next one, capture the next one. You decide what is the speed that you want this video to transition from one to the other frame. And then it creates the MP4. And that's what it's doing in the end. So now we're still creating frames, I think. So we have 60 times.
Yeah, how many did you create?
60 times 6. Apparently.
Okay, 360 frames, fine.
Yeah.
So I have.
That's if you implement it very quickly, you can increase the number very easily, and then it don't test it. So.
So I can. You suggest to put the frame like at 10, not 60.
Yeah, I had it at 2 before, or 1, but then it's a 1 second video or so, and then you can't see anything. So that's why I now increased it once I realized, okay, this is what the interpolate is for. that it takes it's slowing it down a little bit, but that makes it a lot longer to create this. So yeah.
So let me just recap what we. So you change the node size, the color, then you make capture, then you change, then you make capture. So
Exactly.
why?
So you see here.
So why I need to do it 60 times if I only need one change?
It's the frames per second, right, Scooter?
Yeah. It's
Yeah.
60.
So
It's the idea is to do a smooth interpolation, not just change it. So
it's not, but
yeah.
it's transitioning it from one picture to the other. There's a transition, and to be able to see this in a video, that needs to be of a certain length, right? That's how the Cyanimator does this. So we need to give it enough time to transition to be able to see this. So when I do it with one, it's like ding, and then the video is done and it went through all 6 stages and I didn't see anything.
So Martina, what did you suggest to put before and after, like the size and the color? Like you suggest the size and the color?
So what I would actually do, what I'm going to create the script and I'm going to upload and send you an email once it's done. What I would suggest for this example is that you hide. So let's say here I start with, okay, the first frame is lung COVID. So I remove proteins that are not abundant in COVID, so in lung COVID. So the ones that are not, I couldn't find, they're not detected in the lung COVID expression data, protein abundance data. So I remove these nodes, I hide these nodes, and I use the gradient for the how strongly they're abundant. Then I make a snapshot. Then I change my style. I unhide all nodes. All of the nodes are back. I hide the ones that are not expressed in lung non-COVID. Again, use the gradient and make a snapshot. So I capture that frame. And then I say, okay, transition from this to this. And then I see how the network changed from lung COVID to lung non-COVID. Does it make sense?
Yeah.
Okay. And so I would probably make a video per tissue, and the video per category. So I would say you do lung COVID versus non-COVID as one video, and then you could have lung COVID, liver COVID, kidney COVID to see the change of expression across the tissues.
I have one project I am working with. I need to try this one. So I have 2 conditions, the normal and the cancer. Then what I will try to say, like one for the normal, then go to the cancer, and the color things go from gray to red, something like this.
Yeah, for example, yeah. So the more expressed it is, the stronger the color. Yes.
So I can just explain it that, look at this, what happened, this gene is not expressed in the normal, but look at this now, what happened in the cancer, they highly express.
Yeah, I did this once, not automated, but in the app itself for healthy, and then a kind of a pre-disease state, a disease state, and an advanced disease state. So you can look at the progression of the changes, and that some areas suddenly really flame up. So they become light red, redder, with each stage, for example.
Do you have that video?
I can look this one up. I need to check if I find it somewhere.
Thank
Now,
you.
somewhere there should be a video, or it's still creating the video. Let's see. What is it doing now? Is it done here or still running? It looks like it's done. So now I have all the frames, but not the video. Record animation. So it might still be working. I don't know.
Should be done.
It created the video before, so I don't know, maybe. Download test. So it should be in here. but at least I can show you the app now, how this would look here. No, this is still working, I think. I can't click anything yet, so.
Okay.
Mhm. Yeah, this is a little bit worrying now, but somewhere there is an MP4 being created. So next time, for demonstration purposes, less frames. Curious.
Are you hung? Is Cytoscape not responding anymore?
Yeah, it didn't before either because it had the window open. So I
Yeah.
thought maybe it's still exporting it, but now I'm not so sure. Okay, I might stop
Yeah.
this now and just show you how this looks like in the. Let's see.
I can also show my version if you want.
I'll just start it now. So unfortunately, we won't have the video now, but yeah, I think you now would have an imagination of how it would look like. It would paste all these frames together, and it would interpolate from one frame to the next. So from one snapshot, how they call it, or capture
Keyframe.
to the next capture. And this all works with the SciAnimator app. Really nicely. Yeah, obviously now it's disabled, so I'm quickly going to load this network
Yeah,
again.
you need to load a network.
Yeah. Oh, come on. No, everything stopped. Okay.
There we go.
And then in SciAnimator, you basically create the snapshots, the captions, how it's called. So you can change the visual properties and then say, okay, add this frame. And then you change something and you add that frame. And then you change something and then you add that frame. And then you can say, okay, how fast should it be, right? So how much animation speed do you want? And then you export that and record it. And that's the same steps that we did in the program.
Martina, I couldn't see. Could you enlarge the Cytoscape and do it again?
Yeah.
No,
So
no,
let's say.
I mean, if you could just remove the RStudio and just put only the
Yeah.
Cytoscape. Thank you.
So app SciAnimator, and then I clear all frames quickly. I make a snapshot, then I do something here.
Like zoom in, zoom in.
Zoom in, yeah. Zoom in. I make another one. I zoom further in. Now I see something. I make another one. I move around. It doesn't really matter. Another one. And then I can say, play
yeah,
or
just play it.
something. It's going to interpolating the frame. So it's doing the same thing it was doing before, and now you see how it plays. And that's what it would do with the visualizations that we had before, switching between the colors, between the frames.
Got you.
Actually, for zooming, it's a brilliant idea. I didn't think about the zooming one, but that's great. So for video tutorials, for example, or if you want to highlight something in a presentation, you can create a video that shows your big network, and then you zoom into the area that you want to highlight in your presentation. That would be a good use case for this. I'm sure I'm going to use that very soon.
Do you guys have some template, or not template, like style or some examples for these videos in the Cytoscape website?
Yeah,
I guess that on the website of the app as well, right?
Yeah, there's an example on the website for the Cyanometer app. There's also a paper on Cyanometer that
Gotcha.
has some examples.
Oh yeah, my style doesn't exist, so I'm just gonna create a new style. I just want to show the last one really quickly, because I think it's a really nice way to visualize the same data in a different way. And that is, I first need to load the data again because I closed everything down. So now I loaded the data, and now I can apply this. Obviously, you can make this a lot prettier than it is right now. So maybe the default shape should then be a rectangle instead of so it at least fits nicely within it. We realized that this is imported in Paint, Custom Paint 2. Here, there's this heat map. And so what we see is it goes from lung to liver to kidneys, and always COVID, non-COVID. And we have expression up regulation is red, down regulation is blue. And here we have the min and max. So in theory, this is actually just expressions. So we could do from 0 to 1 or something, or 2, maybe 1 to see the differences. So what we now see is this protein, for example, is not detected in many of the tissues. So if I go over here, I see it's not in kidney, it's not in lung, it's only expressed in liver. And in this case, we only look at always only the first one. So this is patient 1 and patient 2 for liver non-COVID, but we only visualized 1. So we see that this protein, CDA, is only detected in liver, but not in the others. These ones are not detected in lung. These ones are not as expressed in lung because it's a lighter color than here. And you can see the changes between the tissues in that way. Maybe you would also, to make it even look a little bit more like a heat map, you could make them even like this, then they're a little bit longer. You can visualize the label on it. So if we select the label and do a pass through, and I can do this programmatically as well, but just to show you how you would do this initially and then implement it. And then you could see how the tissue changes over, how the expression is different between the groups, basically, the different tissues. How it might increase to one and the other. If you are specifically interested in one tissue, then you could, for example, say, okay, let's remove those. And I only look at non-COVID. Let me just check what comes first. Left is COVID, right is non-COVID. So there is more expression in non-COVID and the expression decreases when it's infected. The same here, very strong expression when it's not infected, lower expression when it is infected. Situations like this, right? So you can kind of look what is happening. And much better it would even be if you remove all the gray ones. Everything that's not abundant in any of them, you could remove them and see, okay, for the ones that I do see and that were measured, what changes do I see? And then you could look at this from an overall perspective, basically, because there's a lot of gray here, a lot of proteins that were not measured, which is typical for proteomics data, right? We're not able to measure genome-wide yet.
Martina, I didn't get, how did you only change the level from 6 level to only 2 level?
In here, I deselected the other tissues. So I only select lung now.
Got you.
Yeah, and I could, for example, say, okay, I only want to know kidney and kidney, for example, as an example, and I move those back. And now to make sure it starts from right to left. So this comes first, the COVID comes first, and non-COVID comes second. So from left to right. And you see how the colors also changed now from lung to kidney. And liver is a great example because liver expression is completely different a lot of times because it has a very different function. So a lot of different proteins are expressed that are not expressed anywhere else, for example. And this was a short introduction into advanced graphics, enhanced graphics, I think it's called. That R package that has that app that has a lot of other features as well. So heat map is one of the features of the enhanced graphics app. And then you can save everything, and this gives you an introduction to some additional features that you can use to explore your COVID or other molecular data.
Just to emphasize one point, this kind of visualization is excellent for exploring data. This is not a publishable figure.
No.
It's way too dense. There's way too much information in there. Now, if you had a subset, let's say 10 or 15 that are that are active as part of a particular pathway, and you wanted to publish that so that you could actually see what was going on, then that might be more publishable. But you've got to, your figure has to be readable, and you have to be able to see the data in a reasonable way when it's compressed down.
Exactly. So you need to focus only on one pathway, then you can just, okay.
Probably you'll have to focus on only one pathway, right? You know, but figure you know, think about it for a second. You're probably going to be able to do, yeah, you lost your pathways too.
Mm-hmm.
You're probably going to only be able to do 10 nodes, 15 nodes with a heat map on it. And there's how many nodes in this network?
Too many, 1,023.
Right. So there's 1,000 nodes. So you have to cut this down by roughly 2 orders of magnitude before it's going to actually be able to be something that you can look at in a paper.
So what I try to do is to select all the genes that are expressed in both or abundant in, probably it should be an OR. And then I can use the type as well.
Yep.
So
you want is rather
does
than
not
is
contain. No, that does not work. Yeah, I would do it this way, is and is. So now I selected everything that has data plus the pathways.
Right.
Now I create a new network, and it's still big. So it's maybe still too big for visualization.
But it's single pathway, a single, if you zoom in on one pathway.
But now it gets much more manageable if you zoom in and
you
look
can
at
imagine
some overlap here or something like this. Yeah.
Yeah, exactly. You can imagine some subset of that being a publishable figure.
Yeah. Okay, in terms of time, we only have 15 minutes left. I'm gonna let Lauren very quickly.
Martina, can we know, like, can we get the updated RMD file from you? Because I think
I will make sure that I have all the answers. So I have the runnable versions. I'll upload that as solutions. And I will also make sure that the animation video and stuff is also there. So and maybe do it with the Zoom as an example as well. That's a nice example as well. And also make sure that this visualization with the filtering works. So I'll try to update everything on the GitHub page and also provide the answers for each workflow.
I would suggest stripping that down to 30 frames. It's probably more than enough for some of those interpolations. Yeah, indeed. And maybe only do COVID and not COVID, non-COVID switches. Yeah.
And for the data protein, you said only subset from the large one?
Yeah, so there is I have in the RMD file, there is the link to the paper. It's a really large data set of proteomics data. So if you want to use that for COVID, then you can, it also has a lot more tissues. And they have testes, and they have a heart, and they have a lot of different tissues. So I only use that as an example now.
And where is the citation for that one?
In the RMD file wait a second. It's not in the RMD file. It's in the slides of the introduction workflow.
Okay, gotcha.
Yeah, if you go to the slides for workflow 3, you have the link to the PubMed Central. It's called Multi-Organ Proteomic Landscape of COVID-19, the paper. Great. Then we do a very quick wrap before we go into the Q&A, which will be a little bit shorter than we intended, but we had really good discussions. I'm very happy. Maybe Lauren, we specifically need to for sure mention the survey link that they want us to fill in. So maybe you can share that with them.
Yeah, so I have a very quick wrap up. So I can share my screen. Okay, should be able to see everything, and I can really go through this pretty quick. So, so of course we've been together for the past 2 days doing this, and what do we do? So yesterday we really kind of gave you this little toolbox. So Martina gave you an introduction to the COVID-19 disease maps project and WikiPathways, and then Scooter gave an introduction to Cytoscape and to Cytoscape automation in R. And then today we've really applied this to the COVID data set with these 3 different workflows. So starting with the one on differential gene expression analysis, pathway enrichment analysis, pathway visualization, the second one, and the third. So I don't think I need to go through them. You guys have done them just now. So yeah, so this is kind of what we've gotten up to over the 2 days. And we would really like to have your feedback. So please take that link that was sent in the chat and give your feedback for the tutorial. And so next, I'm not sure how much time we have for this, but I'm going to send, so anybody who wants to see Scooter's talk on single cell sequencing data analysis, stay in the main room. And if you want to have some discussion with Tina about advice for your own research, then go to the breakout room. So everybody will be invited to the breakout room, but just choose which one you want to see.
Lauren, can I ask you, I have a question for you. Do you have some kind of workshop like this? Could you put us in the mailing list if you have something like this?
Yeah, sure. So I don't think there's anything coming up anytime soon that I know of. I have to take a look, but indeed, especially also if you email me, then I can make sure that you're on these lists that you would be aware of any of these kinds of workshops.
How can I get your email address? Like,
I'll send it in the chat.
Thank you.
I think we're also planning on doing, I know Alex is scheduling a couple workshops at UCSF. And it's not clear whether those are going to be online or in person.
That's interesting. You guys are doing great job. We like it.
Good. Glad to hear that. Yeah. Okay. So my email address now is in the chat. So if you want to just shoot me an email, then I can make sure that you're on whichever lists need be. And then I can send, so make the breakout room. So I will see. Okay, so then the room is open. So again, if you want to see Scooter's little talk on the single cell sequencing analysis, then stay in the main room. If you want to discuss with Tina some of your own research, then go to the breakout room.
Yeah, I don't really have a talk. I'm just going to do a demo. Just
Yeah, sorry.
for the
Yeah,
record.
the demo. Yeah.
That's all right. I had several talks on this stuff, but that's boring. We'll just have fun, show the tool.
Something that I quickly want to mention, the GitHub repository where the whole material and so on is happening. So if you, on the front page, there is a link to the contact below where you can also use the issue tracker. The issue tracker is also a way to give, if you have any questions about the workflow that you did, just submit it there. We will get an email about that. We can answer your questions there. And we'll keep monitoring that. So also in the future, feel free to drop questions that you have about any of the things we discussed also there. Or on the mailing list for Cytoscape, if it's Cytoscape specific or anything like this, obviously. I'm going to move to the room in case somebody wants to join me there and has a question that I can help with. Let me know.
Martina, you said in the GitHub page, which GitHub page? The ISMB 2021 tutorial. So how can we?
Yes. So let me see. So now I clicked on. Okay. You have this link, right? This link you've used the whole day and yesterday. At the bottom here, it says if you have any questions, you can either email us if you have us an email, or you can use this issue tracker. And if you're logged into GitHub, you can simply create a new issue and say, I'm trying to run workflow 1 and I'm running into that issue. Can you help me? And then we will get an email about that and we can answer it. And if somebody else has that same issue, they can find this here and see, oh, somebody asked that already. So it's just an open way to.
So you are saying just if we check this website again, we will see the file, RMD file, they are updated.
Exactly.
Okay, got you.
So keep that link to that GitHub page. Exactly. And use the issue tracker if you have any questions. And now a very quick, maybe 10 minutes, 15 minutes, depending on people keep joining, Q&A about different topics. So it was a real pleasure to have you here, and I hope you learned something in case I don't see you anymore. I'll move to room 1 now.
Thank you, Martina. Thank you.
You're welcome.
So I had promised a brief intro into single-cell RNA-seq analysis with Cytoscape. And I got very vigorous last night and decided to start by doing an analysis of a SARS-CoV-2 data set, which has 193,000 genes or 193,000 cells and 37,000 genes. So you can imagine what that matrix looks like. So I'm going to take 2 cuts at this on 2 different computers. It took a long time to process this. The way you use this is it's an app. It's called SC NetViz. You bring this up. This is all of the data that's available in EBI's single cell expression atlas. I just did a search for SARS-CoV-2 or SARS, I think. And I came up with the data set that I'm going to show you and walk through. And it's this data set right there. Gene expression profiling of SARS-CoV-1/2 infected human cell lines. Okay. And you can see there's 197,000 cells. I downloaded that. When I download that, I get this table. Typical RNA-seq data, very sparse. These are all of your standard counts. It also comes down with a number of categories. So including their clustering. So they do clusters at different values of K and the design factors. I went ahead and I did a differential expression based upon the clusters. That's usually what I do. In hindsight, that was the wrong thing to do. I probably should have done it based upon design factors. And when I switch screens, I'll show you that. And there's my differential expression data. So now I have this down to differential expression for all of the genes per cluster. Probably the easiest way to visualize that is with a heat map plot. What this heat map plot is showing you is the top overexpressed genes and the top underexpressed genes per category. And each category is moving along this axis. So what this allows you to do is I can look across and see for these overexpressed genes, what are they doing in each of the other categories? And so I can compare across categories. Okay, that's just a cute little visualization that we did. There's a couple of other plots that are in there. You can also do your standard UMAP plots and all of that on the original data set, colored by category. But this is Cytoscape. Cytoscapes are about networks. So a lot of people do RNA-seq analysis of getting up to this stage where you've got your differentially expressed genes. From here, you can do markers and things like that, but they'll end there. What we wanted to do is pick it up beyond that. And so at this point, I can say, oh, okay, I want to create networks. So for each category, show me how the top 200 genes interact. Okay, so I'll just create networks. Now, of course, this is going to use string, and it's going to download all of the data from string, and then it's going to give me 10 separate networks that I can begin to examine not only the genes, but how they might interact. So I can begin doing much more detailed functional analysis of this data, which is really our intent by this. So there they go. So it's the same kind of string networks that you saw before. And we're going to color those networks by the differential expression. Great. So now we can do all of the kinds of analyses that we saw with strings. So I can take this, I can take a look at all of these downregulated genes, and I can go through and I could say, okay, show me the enrichment for these genes. Bring this table up. This is sort of like the string panel that you saw before that allows you to sort of go through and redo some of this, but it also has some just quick paths. In this case, I can do enrichment. My cutoffs are log two-fold change of 1, which means I have a two-fold differential. And there we go. Now I can see exactly what's in there in this particular, what's enriched in this particular network. Typically, what I will almost always do is I will remove redundant terms and I'll just look at process. It's a better way to look at this. Turn that off, turn it back on. And now I can see my FDR value and what this particular network looks like from this clustering. Now, I did spend some time looking at this data after I had done all of this. This took quite a while on my little Mac here. And during the morning, I reanalyzed the data slightly differently. So I'm going to switch off of here and on to here. So I'm going to change. Oops, and go to a different screen. There we go. Same kind of thing. In this case, what I did when I looked at this data is I found that there was in the data set infected versus non-infected. So there's actually 3 different conditions here. There's the mock data, there is SARS infection, and SARS-CoV-2 infection. And I thought that that would be a really interesting way to examine this data. So That's what I did. I calculated the differential expression and I got this differential expression table. And we can take a look at the heat map plots here. And I found this really intriguing. So here's your mock data right here. And remember that these are in comparison to each other. And you almost see this intriguing gradient of these top genes between your mock data all the way down to SARS-CoV-2. And it gives you the way to sort of explore this and look through it and compare this data. Similarly, here's the networks. If I go to the network visualization, this is SARS-CoV-2. This is SARS. And this is the mock data. And if we go to SARS-CoV-2 and we do the enrichment analysis of that, to nobody's surprise, the top enriched terms are the interferon signaling pathway, immune system process, negative regulation of viral process, interferon gamma, et cetera, like that. So now this gives us a quick way to not only view these, but do functional analysis and begin exploring this data in the context of protein pathways and protein interactions. So that's the high-speed, quick overview of this whole thing.
So, Scott, I have one question. So this list of genes is when you compare SARS-2 versus mock, or it is like when you're comparing so you have 3 columns, each of the column you are comparing with the mock, or?
No, the way this is done is you compare one with all others.
Oh.
Okay. And that's how, because that's otherwise it's like, well, there are ways of just doing this one against this and this one against this, right? But then then mock would never show, right? Because it's always 0. So in this case, it's 1 versus everything else. And that's why you'll see, if I only had 2 columns, for example, they would just be mirrors of each other. Every gene that went up went a corresponding amount down, right? Because you've got the differential expression between those 2. And in fact, the only thing that's reasonable to look at then would just be 1 column, one of those networks.
Got you.
Yep. So.
And the other question, you see that I like the donut plot, but you can say these a lot of colors. How can I see all of this color here? It is like it will be something like for example here we have a lot of Go process.
Yep.
So this color maybe like you have like 15 Go process. So this 15 Go process goes here by 15 color.
So we limit the number of colors. So if you look here on all of these provide the which palette you're using. So you can change the palette, the color palette. You can change how many terms. We're using 8 by default. Okay. And you can change the visualization from a donut to a pie chart to a couple of other visualizations. All right. And that just gives you a way to get some control over it. Generally, too many colors, there's a whole visualization analysis that says if you get too many colors, you can no longer distinguish between them.
Yes.
So 8 is a very safe number.
Mm-hmm.
You can do 10. If you get to 20, you're just going to lose all sense of what's really going on. Now, the other thing that we're doing here in these particular ones, let me zoom in, is you can see the colors are positionally the same. So you've got 2 channels of information that are providing whether this gene is enriched in immune system response or not. right? It's the location and the color. So you can tell that both of these are enriched, all three of these, in fact, are enriched in the immune system response. I keep trying to, the other thing that you can do is I can actually just, if I want to know which of these genes are enriched in the interferon signaling pathway, I can just click it. And those are the ones that are enriched in the interferon signaling pathway. And this is standard string. So string does this, the string app does this automatically.
Gotcha. So just Skylar, just if I have a list of genes, then I need to have Cytoscape network, which shows the pathway and the genes in my list belong to that pathway. So how can I do it using string?
Yeah, in general, I mean, that's what we went through yesterday. In general, I would just do a string protein query. If I have a large gene list, I would put it in right here, right? And I would enter all of those genes in there, and I have a string get a network for me. Then what I would probably do is read in my protein abundance data or my transcriptomic differential expression data or whatever. And I can filter and I can, basically look at the networks, and then I can, perhaps I could select all of the upregulated genes and say, just give me a, just do my enrichment analysis on that, or select all my downregulated genes or filter them out. There's a number of things I can do from there.
But if I am interested in kick pathway, for example.
Mm-hmm. So then again, so for example, in this instance, come here, I'm only interested in KEGG pathways, do my enrichment analysis on KEGG pathways. And, for some reason, herpes simplex infection is the KEGG pathway that comes up.
That's interesting. Oh my God.
Well, it makes a certain amount of sense if you think about it. There probably isn't a SARS-CoV-2 KEGG pathway that's been imported into string at this point. So, it is a viral infection response. So that could make sense. But there you go. There's KEGG pathways. If we can also do reactome pathways instead and see what we have there. And cytokine signaling in immune systems. Makes perfect sense.
I'm wondering, for single cell, how did you do the differential analysis using, did you do it in R or did you do it where?
I basically it's basically written from scratch in Java.
Oh.
So it's all written from scratch in Java. We worked with Gary Bader's lab. They had just published an approach to doing single cell differential expression analysis with filtering. The big thing that you've got to do in single cell data is you've got to do a lot of pre-processing and filtering because it's so sparse. And it's sparse along 2 dimensions, right? You can have categories where this particular gene doesn't show up at all. You can have cells where almost no genes show up. So you want to just toss out those cells. So if you look at if I come back here to this category, you can see that I'm getting a log2 fold change and a min %. And that min % is basically working on how many genes are available. And you can sort of how many genes and how many cells per gene. And sort of this value allows you to do that cutoff. And we're using a log2 fold change cutoff here of 0.5 when we calculate the differential expression. But when I create the networks, I typically do a log2 fold change of 1. So I'm looking at a doubling of the fold.
Is it public, this JavaScript? Is public?
Oh yeah, it's all in GitHub.
So what they called it?
This is called SCNetViz.
Okay.
And if you look on the App Store, there's a pointer to the source code.
Thank you very much.
Sure.
Thank you for these 2 days. It has been, a lot of information, but it was really good. And I enjoyed the tutorial a lot. So thank you so much.
Great. Thanks for coming.
Thank you. Bye.
It could definitely be.
Yeah,
the
thanks
case.
everybody. And again, if you want me to put you on the list, then please just send your emails in the chat.
Yeah, please. Thank you very much. Thank you guys. Enjoy your weekend.